All right, here we go. In your exercise book, I want you to copy this formula here. It's not a formula, it's really just trying to break it down so it's easier for you to understand the parameters or things that changes the graph. So you've got B, and I do want you to write it in that particular order, and I'm going to break it down so that you can see the difference. So have a go, write it down first. Y equals B times A to the power of X plus H plus K. Let's go, write this down. Write down your general formula. This is a general formula for an exponential function. And I'm going to relate it back to what you've learned with turning point form, with inflection point form that you learned from last term. And then we're going to look at some of the graphs and some properties. Okay? So this is 13C. This is exercise 13C. Here you go. Just write down the rule first. The examples here, I'm going to guide you through it. I'm just going to guide you through what is the difference between y equals 2 to the power of x, 3 to the power of x, 5 to the power of x. Okay? This is exercise 13C, and it's the graph of exponential. Yeah. So exponential graphs. If you were to title it, exponential graphs 13C. What I've written up there is not in your textbook, so that's why I want you to copy it down. That's just how I'm going to explain it to you as an overview. Now, once you've copied it, what I want you to understand is this is like your chapter 4, or was it 5? 4, where you had a gallery of graphs, and I would give you the basic graph, and I tell you can move it up, down, left, right. This is the same thing. Okay? So let's do a comparison. You would have seen in chapter 4, y equals to 1 on x. What is this function called again? Hyperbola. Very good. Okay, rectangular hyperbole. So this is what it looks like. So when I gave it to you, I gave you a general shape. So I said for a general 1 on x function, which is a rectangular hyperbole, it looks like this. Then I said that some of the key properties that you had were 2 axis asymptotes. So there are 2 of them. This has the horizontal asymptote at y equals 0 and vertical at x equals 0, right? What you learnt in that chapter was something that looked like this. I would say, what happens to the graph if I add a 3? What would you say? If I put a plus 3 there, what changes in that graph? The y function. Y asymptote, very good. It actually shifts up by 3, okay? What you'll find is that in exponential, it is the same thing. Whatever you applied and learnt in rectangular hyperboles or square root functions or quadratic graphs, it's the same thing that applies to exponential. So here is your basic exponential graph. That's a basic exponential graph. Now notice I used the letter A because the letter A represents what the base value is. So it could be 2 to the power of x, that's an exponential function. It could be 3 to the power of x, that's an exponential function. So what you see here is what does an exponential function look like? As a basic look to it, this is what it should look like. And it should have a horizontal asymptote, and only one. A lot of students write 2 of them, so they do another one here. There's no 2 asymptotes, there's only 1. So it's your horizontal asymptote is at y equals 0. Now, there is one more property that you must have. So if you're copying this down, y equals a to the power of x. With that general graph that you have, I do want you to always make sure to label is the y-intercept. Now this one, doesn't matter what a is, they will all have the same y-intercept. What would the y-intercept have to be? Andre? Why?
Anything to the power of 0 is 1.
Very good, Set. If I backtrack a bit for those who are a bit confused, when I ask for the y-intercept, how do you normally find the y-intercept? What do you have to do?
X equals 0.
X equals 0. So that means if I let x equal to 0, you would end up with a to the power of 0. Now what's a to the power of 0? 1. We know from our index laws that anything to the power of 0 is 1. So it doesn't matter what number I choose here, whether it's 3 to the power of x or 4 to the power of x. When you substitute x equals 0, the y-intercept has to always be 1. So hence the property should be 0, 1. The only time that changes is if you move the graph. So if you move it up or down, that's the only time the y-intercept would change. Or if you move it left and right, that's the only time the x-intercept would change. But otherwise, with no other transformations than just the way it is, naturally you should only have a y-intercept at 0, 1. So with these examples below, so I've got 3 different graphs there. Y equals 2 to the power of x, that's an exponential function because it's to the power of x. That's an exponential function. That's 3 to the power of x. Then I have 5 to the power of x. So they all have a 0, 1, which is the coordinates for the y-intercept, which are all the same, but they have to be different somewhere. Now this is where I want you to predict 2 to the power of x and 3 to the power of x. What's the difference between the two if they both have this same shape? How would you show them differently on a graph, logically? If you were to predict, how would they look different?
You can kind of grow faster because higher base value.
Okay, now, well, you said higher base value, it'll grow faster. What do you mean by that?
You still have the 0, 1 intercept, but I guess you can like make it more steep.
Very good. So this is where I want you to think about it on a logical basis. 2 to the power of x just means 2 to the power of 1 is 2. 2 to the power of 2 is 4. 2 to the power of 3 is 8. All you're doing is you're doubling it. So double 2 is 4, double 4 is 8, double 8 is 16. So what you're doing here is you're doubling. So I'm going to write here doubling. When you do threes, indices of threes, you're doing 3 to the power of 1 is 3. 3 to the power of 2 is 9. 3 to the power of 3 is 27. What's happening? You're tripling. So when you do a base 3, what you're actually doing here is you're tripling. So what should you expect is the graph, if this was the graph of 2 to the power of x, then naturally 3 to the power of x has to be steeper. Because when x is 1, 2 to the power of 1 is only 2, but then 3 to the power of 1 is obviously larger. That's why it looks steeper, right? Now what's interesting is the other side. If you substitute a negative number now, and I want you to think about it on a logical sense, because this is what methods is about. It's about you analyzing that function. If you have y equals 3 to the power of x, and you have y equals 2 to the power of x, if I substitute a negative number, say x equals negative 1, this is 3 to the negative 1, this is 2 to the negative 1. What's the value? Using your index laws, what's 3 to the negative 1 the same as? 1 over 3. So remember, negative indices, you can do the reciprocal, becomes 1 over 3, and over here this would be 1 over 2. Now out of the two, which one's bigger? Half is bigger. So what was interesting is if I substituted a positive number, x equals 1, you end up with 3 to the power of 1, and the other one was 2 to the power of 1. So this is 3, this is 2. So you would say 3 is bigger. But then on the negative side, notice half is bigger. So if you use that sort of understanding, when I substitute into the graph here, so I'm going to zoom in just so you can see, it made sense that when x was 1, this would be 2 to the power of 1, which is just 2. But for the second graph, we knew that when x is 1, 3 to the power of 1 is 3, so it has to be bigger. So that's why it looks more like that. So this is your 3 to the power of x, this is your 2 to the power of x. But what happens when you substitute a negative number? We notice that when it's negative, the red graph ended up being a third, whilst there's the black graph, or the one with a base 2, ended up being a half. So what actually happens here is that when this is 1 and the 2 is half, the red graph ended up being smaller. So it ends up being a third. Negative 1 is a third. Okay, so that might be a bit hard to see there, but what I'm trying to show to you is this. So if you were confused about what I was saying, I'm trying to say this is 2 to the power of x, then the difference is that 3 to the power of x will be steeper when it's positive, but yet it'll be smaller in the negative region. This is 3 to the power of x. So then when you go to 5 to the power of x, what you should expect is that the graph should be steeper than 3, but then smaller than 3. Sorry, that's a very bad graph there. I'm just going to fix that. There we go. That's what it should look like. Okay, so if you were to write anything right now as part of your notes, what is the difference between 2 to the power of x, 3 to the power of x, 5 to the power of x? It just changes that steepness from the right-hand side to the left-hand side. That's the difference. Okay, so what is this telling you? That means when you change the value of A, that's what you should see the difference in the graph to be. That's the main point. Okay, now in year 12, they will focus on what the A value is. So something like, this is one of the multiple choice questions in year 12. They ask you, what does changing A do? Okay, so then you would say it makes it steeper or less steep in the negative side. But then the next question is, logically, what can't A be? Can't be 0. Why? Because you're right.
Can't be equal to the power of n.
Yeah, because 0 to the power of x is what? 0. 0 to the power of anything is 0, because 0 to the power of 1 is 0. 0 to the power of 2 just means 0 times 0. So it should be 0. But if you were to sketch that graph, what would the graph look like? Yeah, it's just a nice normal line on 0. This is what it would look like. If you were to sketch a 0 to the power of x graph, all it just means is when x is 1, you have 0 to the power of 1, which is 0. When x is 2, you have 0 to the power of 2, which is again 0. When x is 3, 0 to the power of 3 is also again 0. So if you connect it, it just ends up being a horizontal line. And that's a problem because that's not exponential. Exponential follows this property with an asymptote. So A can't be 0. What else can't A be? 1. Why can't it be 1? Very good. So what kind of graph would you expect if it was 1? Yeah, horizontal line at 1. So if you tried 1 to the power of x in your graph, you should expect a nice horizontal line. And that's what I'm going to show you over here, Desmos' graph. Is it that one? No, this one over here. You see A, that's your base. I've pretty much typed up what I gave to you as your transformation. Watch what happens when I change that A. See, A is currently 2, but if I change it to 1 now, see, I'm going to drop it down. And you see that 0, nice horizontal line on 0. And then if I make it 1, you can see that it's also another nice horizontal line at 1, because it makes sense. What else can't it have? So it can't be 0, can't be 1. What else can't it be?
Negative 1.
Negative 1. Also?
Infinity. It's like...
You can have infinity. It's just a very large infinity. Just looks really bad. So you got 0, 1, what else?
Wait, any negative number?
Any negative number. And why is that? I want you to think about it before you answer that question, because that is a typical year 12. If they ever chuck it into a multiple choice question, they will ask you, it's only 1 mark as well, why can't it be negative?
Because every x makes the graph.
What do you say?
Yeah, very good. So that's what I want you to think about. That's what methods is. It's about you analyzing each parameter. For those who don't know what it looks like, here we go. I'm going to show you what it looks like. Okay, so here we go. Control I, I'm going to add on a graph. Let's try negative 2. So you need to put in brackets so the calculator knows it's negative 2 to the power of x. So the base is negative 2 now. And you watch, if I press enter, see that graph? Now why is this happening? You see, it looks cool, but technically there is an error here. You see, there shouldn't be any vertical lines. Because every single coordinate, remember when you sub in 1, in 1, when you do a power of 1, x is 1, and then you do, if it's negative 2 to the power of 2 becomes now a positive value. And then when you have 3, negative 2 to the power of 3 ends up being a negative value. So what happens is it goes positive, negative, positive, negative. Every time the power is a nice even number, it becomes positive. Like 2 squared, 4 squared, anything squared has to go positive. Then any odd power, it drops down. So it actually ends up being a nice vacuum that goes up and a vacuum that comes down, but they're dots. There is no connecting line in between them. Okay, so this is not an exponential graph. So hence, if A is negative, A is 1, or A is 0, it can't exist. Andre?
So like negative 2 to the 1/2 wouldn't exist?
Negative
Because that would be
2,
the square root of minus 2.
correct. Well, unless you work into complex numbers.
What if you had the square root of, what if you got to the cube root, so like negative 9 to a third? That would be on the graph.
Yes, but that would be a different, negative 9 to a third.
If you had y equals minus 9 to the x,
I think that's right.
yeah, it would be 3.
Correct.
So there would be dots in between.
That would mean that, yeah, the problem is that overall it's not going to be an exponential graph, though. So for that particular value, it works, but then for all values, it doesn't work. Does that make sense? Yeah. So then in terms of exponential, which is what this chapter is about, then it can't be any negative values, can't be 0, and it can't be 1. Okay? But it can be half or a third. Why is that? So this is now, I'm pushing you guys a bit. It won't be tested in this exercise in this unit. But why can I have a equal to, say, a third? So for example, that would mean you'd have a third to the power of x. This is possible to sketch. Why?
It's equivalent to like 3 to the power of minus x.
Good. So using your index laws, 1/3 is the same thing as writing 3 to the power of -1, all to the power of x. And using your index laws again, -1 with the x on the outside, you can multiply the powers, and it's 3 to -x. That is possible to sketch because the base value is a 3, and that's just a reflection. Okay, so if I put in a third right now for you to see, oh, not that one. If I put in a third, so A is, let's just go 0.25, that's best. Can you see how there's a reflection now? It's gone the other way.
Wow.
Okay, yeah.
Would that still be an exponential?
It is still an exponential. It's just that it's a reflection across the y-axis. Okay, so all the decimals in between 0 and 1. So we said it can't be 0, can't be 1, can't be negatives, but what about in between? It's just essentially a reflection. So you notice that if I keep it 0.25 to 0.5, it's still in that reflection zone. But once I hit 1, it's 0. And then watch what happens once I pass 1. It's okay. So it becomes an exponential, but reflected on the other side. And the more you increase the value, the steeper it just gets. That's all it does. Okay? So that was a lot to really get you to understand the idea of what the base A value does. If you don't get it, it's okay. It's not part of the Unit 2 at the moment, but it is your critical thinking for Unit 3 and 4. Okay? Now, let's use what you've learned so far with exponentials. So all your transformations, you've got an idea of what it looks like. Let's go back here. I'm going to go back here. So we now know what A does. What does changing K do? What does changing H do? And what does changing B do? I think most of you will understand H and K. It's the B that I want you to think about. So here we go. This is my graph. K. K is the number that you're adding on the outside. Let's see what happens when I change K, and then you tell me what happens here. Okay, so I'm going to change K. Going to 0.25. 1.25. 2.25. When I change it to, say, 5, okay, when I change it to 5, can you see what's happening to the graph right now? It's going up because the value that I'm changing is a positive value. So when it's 5, it's a positive 5, so it shifts the graph up by 5, but not only that, the asymptote is at 5. Okay, so that means the graph will never touch 5. It will always get really close to 5. So if I zoom in, you can see here it never touches that graph. So I'm zooming in. Oh, actually, I know, it was terrible. I think that was zooming on the page. How do I zoom in on the graph? Oh, there we go. So I'm zooming in. Can you see it doesn't touch? The more closer I get, there's a gap between that. So I keep zooming in, and you can see that there's always a gap between that graph and y equals 5. Okay? So we know K shifts the graph up or down. Let's have a look what happens when, sorry, how do I get it back home again? There we go. All right. Let's see what happens when I change the graph now to, instead of K equals 5, let's see what happens if I change it to negative. So you can see up and down, all I'm doing is negative, positive. It just changes up and down. That's all it does. The shape stays the same, but the plus K shifts the graph up or down. That's all it does. Okay, so in your notes, I want you to have what does K do? K is this value over here. That moves the graph up or down. Okay? What about H? What does H do? Let's have a think. Where's my equation again? I'm going to go press home. Translation to the left or to the right. Very good. So exactly what you've done with with quadratics and cubics. This is what I want you to see. So here we go. I'm going to move H. So watch. I'm going to move to 2. So if I change it to 2, see it's moving to the left. So when the value is positive, it moves to the left. When it's negative, you find that it ends up moving to the right. So I'm just moving it left and right. So when you look at an equation, you should be determining, are there any x-intercepts? Are there any y-intercepts? Now in this particular graph, is there ever a time where you will not have a y-intercept? Never. You will always cross the y-intercept. Okay, so you always should have a y-intercept. What you may not have is an x-intercept. How does that occur? Well, if you just change k. If I shift it up by, say, 2 or 3, you can see that that graph will never touch the x-axis. Then there's no point in you trying to figure out the x-intercept. Okay? In terms of the asymptote, so you should always have the asymptote. What else also changes? Your y-intercept. Your y-intercept now is no longer 0, 1, but it is now at whatever the new equation is. Okay? So, all of these were easy. H, K, A, now B. Based on what you've learned from chapter 4, B is a multiplication term. So what does that do to the graph?
Changes the gradient.
It does change the gradient, more so the steepness of it. Okay, now what's the difference between B, so changing it this way, and then noticing I haven't put an extra term here, but I'm going to put another term here. I'm going to call it C, because I haven't used C yet. So I'm going to add in a C. Notice where I put that C value. C, I put it right next to the X. So you can either multiply to the X, or you multiply B to the function. So there's a difference. You either multiply B to the exponential, or you multiply C just to the X value. So I want you to have a look, and then you tell me, what do you think when I change them? So I'm going to change this all back to 0, just so everything's all nice and steady right at the center. There we go. This is your typical exponential graph, where A is 2 and B is 1. Watch what happens when I change C, and then I change B as well. Okay, so I'm going to change C first. C is the value in front of X. Okay, C is the value in front of X. Watch what happens. So I'm going to change, have a look, and I'm going to go back. I'm going to do it again. I'm going to come back. Look at the y-intercept. What's happening to the y-intercept? Is it still the same? Is it moving? Okay. Now, I'm going to change the B term. And I want you to tell me what is the difference between the multiplication of the function or the multiplication of the x values. Because that applies to all functions and not just exponentials. So here we go. Let's have a look. I'm going to change B. B up. B down. Oh, sorry, let me just put it down again. B up. B down. Okay. And then I'm going to go back now to C again and tell me, can you see the clear difference between it? Because they're both stretches. Multiplication is a stretch. But you need to know, is it a vertical stretch or a horizontal stretch? I can't get it back to 1. There we go. So I'm going to change C again. So this is C. And I decrease it. C. Decrease. Now you tell me. Difference between B and C. They're both stretches, but what kind of stretch? Is it which one's the vertical, which one's the horizontal?
So the B changes the asymptote as well as the gradient. Not the gradient. It doesn't change the gradient. It just changes the asymptote.
It's not that much
It
pressure.
affects everything,
It only affects
all
one or something.
values except K. And then the C affects the gradient.
Very good. I think everything was correct except for one thing there, but Jacob